There we go. And okay. So this week we have the pleasure of having our good friend Himanshu Singh speak to us. He's going to be speaking to us, well, I think about these series. He's also going to speak about well, a bunch of function spaces of analytic functions in the disk. So without any further ado, Himanshu, it's all yours.
Okay, hello. Hello, everybody. So today I'm going to talk about this trifecta of Hilbert spaces on unit disk. And these are Hardy space, these are Bergman space and Dirichlet space. So before going further and before discussing that what I'm going to talk about, I want to have, I would request everybody to have a look on this slide 1, where I would request everybody to compare between these two quantities. And the first quantity says that you have a summation which is like 2 over n factorial square multiplied by n plus 1, and the second one is summation n plus 3 over n factorial square n plus 2. So this is the first quantity that I would request you to have a comparison between these two things. And this is the second quantities which I would request to have a comparison. And I would ask that, like, according to you, uh, which one of the side is bigger, like left hand side is bigger in quantity 1, or right hand side is bigger in quantity 1, or maybe like left hand side is bigger in quantity 2, or maybe the right hand side is bigger in quantity 2, or both of them are equal. So if you have if you're fine, then I mean, obviously you can discuss the answer right now, and then probably I will let you know the right answer during this course of presentation. So is there anyone who wants to present his or her answer during this moment?
Well, I have a guess if no one else is going to. My guess is that, at least for the first one, it looks like the one on the right will be bigger, and I guess same for the one on the, well, maybe the one on the left will be bigger for the one on the bottom, it looks like, at least. Although I think
Okay. Okay. So, I mean, you think that for quantity 1, the right-hand side would be bigger, and for quantity 2, maybe the left-hand side would be bigger, right?
Sure.
That's what you're saying?
Yeah.
Okay. So we'll see that what is the right answer for these two problems during the course of presentation, and we'll hold for the right answer just for maybe for a little while, and then see what we can do in this. So before discussing the solution of this problem, I want to have a recall for what is the definition for Hardy space, Bergman space, and Dirichlet space that I'm going to use. So so we have a holomorphic function on the unit disk U, and I'm presenting the unit disk with U, and I'm having this infinite series expansion as a n z to the n, where obviously n belongs to the complex numbers and everything. So we know what is Hardy's space. The Hardy norm for f is given as the summation of an square, obviously to be finite less than infinity, and with respect to the integral representation, we have 1 over 2 pi. You take the integral from minus pi to pi of f of e to the I theta absolute squared d theta. So this is Hardy norm. And if you talk about Boltzmann norm, we have this thing, summation n square over n plus 1. And in the integral representation, we have 1 over pi, and you do the integration of f to the z square absolute over u with respect to the area measure. And when you talk about the Dirichlet, we have these two things, summation like a0 absolute square plus the summation from 1 to infinity n square multiplied by n. And when we do the integral representation, this thing becomes this thing is done as 1 over pi integral u of f prime of z square dac. So one more time, we have to be careful that we see that in Hardy space during the discussion that when it is represented in the integral manner, we have d theta. It's like just like a linear measure, right? As compared to Boltzmann or Dirichlet, where we have area measure, right? So there is a difference between length measure and an area measure. Now, moving further, so there is a striking, there is a it's kind of an important equality, or it's kind of like an important identity for Hardy space, which is called as Littlewood Paley equality for Hardy space. So it says that the Hardy norm of F is equals to the F0 absolute square plus this thing plus 2 over pi integral over u f prime of z squared absolute multiplied by log of 1 over absolute z with respect to the area measure. So I saw this equality maybe in the last semester while I was doing some kind of operator theory work with my advisor, Dr. Joel. And I was just I just got this equality on some paper of maybe P. Borden or maybe Joel Shapiro. So, and then I saw this equality, and I mean, at first, this equality was like, very abstract. But later on, I realized that this equality has the potential to connect the Hardy space norm, which has lengthwise measure, like a linear measure, with respect to area measure. Oh, sorry. With respect to area measure, right? So I thought that this is literally like this is quite important. This is something little new for me. So, and then I thought that what could be more usefulness that can be extracted from this equality. So then I realized that this particular function, which I am encircling now, this log over 1 over z, this is quite important. And why it is important? Because it is used in the Nevanlinna counting function for Hardy space. And I'm going to talk about more of this Nevanlinna counting function in a little while. So now the question comes that, is it possible to produce this type of equality for Bergman space or maybe for Dirichlet space? And if it is possible, then do we know about it? I mean, is there already like there on the internet? Maybe has someone already done this thing for Bergman or for Dirichlet? Yeah.
What? So is it possible to have Littlewood Paley equality? So or equality. So what do you mean by that?
So I mean, I wanted to know that that this is when we see that Littlewood Paley equality for Hardy space, we see that like there is an identity for Hardy norm, like this thing, right?
Mm-hmm.
This is directly represented as 1 over 2 pi minus pi to pi of f of e to the I theta square d theta, and this thing is ultimately equals to f of 0 squared, like this whole thing, right?
Sure.
So I mean, I was curious that if you talk about Bergman space, so Bergman space is this thing, right? Mm-hmm. Right, this is Bergman space, right?
Mm-hmm.
And this thing is equals to 1 over pi when you do the integral of u over u of f of z squared with respect to area measure, right? This is how the Bergman norm, Bergman space norm is related with this thing. My curiosity was that is it possible to give this kind of presentation that we have for Hardy space for Bergman space? You see what I'm saying? That is it possible?
In terms of arc length measure, or in terms of what?
No, just go on, like just go with the area measure, because I don't know what would be the direct replacement for the area measure or something like that. But I was interested in having a presentation that, okay, let's try to present this thing with the f of 0 squared plus something multiplied by like integral with respect to u of f prime of z squared multiplied by some quantity, so that this whole thing looks like this summation of n over from 0 to infinity n square over n plus 1. And the same kind of curiosity was there for Dirichlet space also.
Okay, so
Is it okay? You see what I'm saying?
maybe I guess I'll see.
Yeah. So actually, I wanted to have another kind of presentation as it happened in the Hardy space, and uh, and I searched for like numerous type of articles related to various kind of integral representation for for Bergman norm, for Dirichlet norm online, and whatnot. But to be honest, I didn't think that I was able to find the right kind of answer which I was looking for, which is why and all this thing happened during this this last scene that happened in the month of March 2021, and but unfortunate but like fortunately or unfortunately, I got to know that it is possible to produce this kind of equality for both of the spaces, and and once I found this type of equality, then I was little curious that is it possible to produce this type of equality for Fock space, or maybe for Mittag-Leffler space. And for Mittag-Leffler space, I would like to just give the introduction over here. So for Mittag-Leffler space, again, it's a like RKHS as all this Hardy, Bergman, or Dirichlet are. So this is given as the norm of Mittag-Leffler is given as in this manner: 1 over q pi, this you see q is always greater than 0 over complex plane, and so the measure the weight is here like this. Okay, and if you put q as 1 in this Mittag-Leffler norm, so you will come back to the Fock space. So in other words, you can say that Mittag-Leffler space, ML2 space, is one parameterization of Fock space, and it was constructed by Dr. Joel and his collaborators in the year 2018. So it is used for the study of fractional order calculus, so it's a RKHS, it is a reproducing kernel Hilbert space, but as of now, our major concern is this: that is it possible to produce this type of equality for Mittag-Leffler space? And obviously, if you are able to construct this type of equality for Mittag-Leffler space, then it's needless to say that you have constructed this type of equality for Fock space, because as I said, Fock space is a one parameterization for Mittag-Leffler space. So by putting q as 1, you will come back to the Fock space. So you are done. So during this whole presentation of mine, I'll produce this type of result that it is possible to give the Littlewood Paley identity for Mittag-Leffler space and for Fock space, and so now let's go further and see that what is the Littlewood Paley estimate for Littlewood Paley equality for Bergman space, or maybe for Dirichlet space. So for Bergman space, so the equation 1 that I have written over here, so this thing is, I think this should be the Littlewood Paley equality for Bergman space. And when you talk about for Dirichlet space, so this thing becomes over here, the equality that I'm writing over here is going to be the Littlewood Paley equality for Dirichlet space. So let me read it further. So for Bergman, I'm presenting, as I told you earlier, that I'm presenting with A to U. So the norm of Bergman is equals to f of 0 squared absolute, plus you take the integral of f prime of z squared multiplied by this weight. Okay, so the weight is here, that is absolute of z squared plus 2 log 1 over z minus 1 with respect to, again, area measure, and you take the mean as 1 over pi. Okay, and when you talk about Dirichlet, so we have this thing as f of 0 squared plus f prime of z squared, but here we have double derivatives. Okay, so 1 over pi integral of this quantity, which is f double prime of z squared, multiplied by the same thing which was present in the Bergman, and you do 1 over pi as the mean. So this is, when I saw these two equality, I realized that it's quite important, like to notice this fact that this weight, which I'm encircling in blue, is present in both of the equalities. This thing, this is present in both of the equality. And there's kind of a pattern that, okay, in the Bergman you have f prime, you have single prime, but in Dirichlet you have f double prime, right? And f of 0 is squared is okay, it's present, and you have f prime of z f0 squared, which is quite needed for Dirichlet norm, because the summation starts from n equals to 1, right? So I mean, this was quite interesting when I compared these two equalities at a time, that the weight are present, the weight that are present are like same, which is z squared plus 2 log 1 over z minus 1. And I mean, I was worried. I was not worried, but I was like little confused, and I wanted to know. I just got curious that what this is actually. I mean, what does it mean that this absolute of z squared plus 2 log over z minus 1 is present? And both of them are like, again, same thing. And then I wanted to do more, and in more like in the sense of this more word, I meant that is there any connection between these two, or maybe between these three spaces? So I want to share one anecdote between me and Nathan. And I hope you remembered this thing that hey, I said, Nathan, that hey, I think that these three spaces are connected with each other. And I said that hey, we have this thing that n from 0 to infinity an squared multiplied by n plus 1 to the alpha, right? So when you put alpha as 0, you get Hardy space. When you put alpha as -1, you get Bergman space. When you put alpha as 1, you get Dirichlet space. I think you remember, Nathan, this, right?
I remember.
We did this thing in our TA discussion room in top stair in the first floor, right? You said this thing.
I remember.
Yeah. So and then you asked me that what is the importance of your connection when we already have this kind of connection, that you just plug different values of alpha, you get the different types of spaces. And it was quite an important question to come up to me. I'm going to answer that question in just a while. But before, I would request to have a look on this thing, that the connection between Hardy and Bergman, and the connection between Hardy and Dirichlet. So equation AH is a direct connection between Hardy and Bergman, and equation DH is the direct connection between Hardy and Dirichlet. So what you are seeing here, you are seeing is that in the first equality, which is AH equality, if you have this type of equality, then you can connect with Hardy and Bergman in like in a simultaneous manner, right? I think simultaneous is not a good word. It's not a good choice of word, but I mean, you can see the connection between Hardy and Bergman with this equality, and the same way you can see the connection between Dirichlet and Hardy with this equality. So and again, you notice that 1 minus z squared, this again the right kind, the factor which is multiplied by f prime of z in AH equality is same as this thing which is present over here, multiplied by f double prime of z in the DH equality. So again, this same thing, again the same confusion, the same question came up, that what does this thing mean? What is this this thing doing over here? What is the practical meaning of this thing? So I don't know what one more article I was studying online, but I got to know about one more space called as Bloat space. I think I said this name correctly, maybe Bloch or maybe Bloch. But when I was studying about this Bloat space on maybe I think obviously Wikipedia, so I noticed that the norm of Bloat space is defined some with respect to like the soup of I think some integral of function multiplied by 1 minus z squared, this thing, right? If I'm not wrong, so something, this thing is present over there in Bloch space, or whatever. So at that point of time, I thought
this is actually not correct. Bloch norm is supremum without any integral. It's just the rate of growth of the derivative of the function.
So it's okay. I apologize. So the integral is not there, but f prime is there, right?
Yeah, f prime is there.
Okay. Okay. I apologize for this confusion. But I mean, yeah. Thank you for clarifying this thing. So again, but here is the point of observation that you see that 1 minus absolute of z square is present in Bloat space. So I mean, I was quite intrigued at that point of time that it looks to me that at least in some sense that all these four spaces are connected with each other in one or the other way. But as of now, I have I have the connection between these three spaces, between Hardy, between Hardy, Dirichlet, and Bergman. I don't have any connection with Bloat space as of now, but I have. This is going to be like my future study if
I'm sorry, it's Bloch.
Yeah. Bloch.
Henri Bloch. He's a French mathematician.
Okay. Thank you. Again, I apologize.
Too far. I have a question. Could you scroll back up to the previous slide, I think?
Yeah, okay.
Yeah, so these two formulas that you wrote down, how were they derived? It looks like just some sort of integration by parts. Is that correct? Or how are these formulas?
It's okay. So how if you ask about how I derived this thing, it was quite a like laborious task, because you said this thing called as like Hausdorff moment problem. Or maybe like inverse moment problem. So I studied a lot about these two things in order to search the right weight of this thing, in order to search the right weight, which is this thing. So I searched a lot, and it doesn't involve this integration by parts. It just involved this maybe inverse moment problem, you can say, or maybe Hausdorff moment problem. So the good thing is this, that we have a definite integration between 0 to 1 when you go from this complex when you change the whole this substitution, like this polar coordinate expression from 0 to 1. So we have that good thing that we will do the integration from 0 to 1 in the area, in the R limit. So that is a good thing. But it's not quite as you think that it involves integration by parts. But it's like it was quite a like hit and trial that what kind of a function would.
And I'm sorry again to interrupt, but yes, Nathan, you can do it very easily by integration by parts. That's how Paley Littlewood is done, and because you have a function which is basically vanishes on the boundary, and integration by, I mean, you have to tune the coefficients, so, and you do it for polynomials, and that's it.
Yes. Yeah.
And then by density or some density. Okay.
Okay. So this AH equality. So this AH equality it gives you the connection between Hardy and Bergman, and this DH equality gives you the connection between Hardy and Dirichlet. So as of now, we can see the connection between between Bergman and Dirichlet, and we can see the connection between Dirichlet and Hardy. So now my question was this, that is it possible to connect all the three spaces a single equation? So the answer is yes, and that equality is I'm calling as a master connection, and this is the master connection that I have. So the summation of Bergman and Dirichlet norm is going to be the summation of these three things, which is f of 0 square absolute plus Hardy norm plus 1 over pi integral over u f prime of z square multiplied by z squared with respect to area measure. So I thought maybe this is like good for this whole like tricks or something like that. I thought is to implement with any like holomorphic function with some entire function. So I played with this equality with sine z.
I'm sorry, again, I have a question. So what does a connection actually do? Because the sets of functions in different spaces are completely different sets. there is a strict inclusion. Dirichlet is the smallest, Bergman is the biggest. So this is, I mean, this is for essentially for polynomials it works, but other than that, they consist of very different sets of functions.
Okay. Yeah. I mean, I'm not sure that what this can like where all these things can be right, because it's like it's like a very few
Well, they're correct. If you take a function in the smallest space, Dirichlet space, which is the smallest one, then it's correct. But other than that, it's not. It's because of the
containment of the spaces.
Well, you can have
yeah. So I mean, during this whole whole idea evolution, when I was doing all this thing, so I wasn't sure that, I mean, where I'm leading to. So the only thing that I had with me was that like, is it possible to create a connection between Hardy space among Hardy, Dirichlet, and Bergman? So I mean, since obviously if I take a function from
I'm sorry, it's also Bergman. It's not Bergman. It's Bergman. Stefan Bergman.
Okay, Bergman. Apologize for that. So yeah, so is it like the only question was that, is it possible to have a direct connection with Bergman, Hardy, and maybe and Dirichlet in just like one single sitting? So I mean, right now, if we take any function from Dirichlet space, then obviously this thing will be right, and because as you said that Dirichlet space is the smallest space of all three. So I mean, it all came up as a corollary, something like that, when I was trying to work with the Littlewood Paley equality for Bergman and for Dirichlet. And I don't think that is I don't have any other visual of importance for this equality. But as I said, that when I wanted to explore something, so I just played with one holomorphic function, one entire function, like let's say f as sine z, and then I got, okay, so yeah, this result was true. I mean, obviously, for when I played with f of z is equal to sine z in this equality. Yeah,
that's sort of an interesting application, and I guess you can derive sort of unexpected looking series equalities.
Yeah. That's right. And I'm now I'm going to give you the solution for the first for the question that I asked in the first slide.
So I have a question. Yeah. So it's kind of in regards to what Dima was saying. So if you take a function which is in one of these spaces but not the other, so say it's in the Dirichlet space but not in the other two.
Yeah.
And you write down formally all of these sums. Does it count as or does it coincide with a regularization of that sum?
So I'm not sure about I'm not sure about this thing, that will it be possible to have that type of equality for the function which lives only in Dirichlet, not maybe in Bergman, and not maybe in the Hardy. So I'm not sure about that thing. Maybe
no, you just each time get infinity is equal to infinity.
Well, if it's in one space, though, suppose it's in the Dirichlet space and say also the Hardy space. Well,
in Dirichlet space, it's already in all three of them. Dirichlet is the smallest.
So you have to take something that's in one but not the other two, then I guess. So you'd have to take something that's in maybe Hardy space, I guess.
Well, if you take in Hardy space, then Bergman space norm is going to be finite. Dirichlet norm, if it's not in Dirichlet space, is going to be infinite. And therefore, this norm is going to be infinite as well. So it's infinite. It's infinity. It's a correct equality which for polynomials which are dense in all three, and therefore it extends to infinity is equal to infinity.
Okay, so it doesn't work as vectorization technique, I guess.
Yeah, and certainly you can get a lot of equalities for power theory.
So this is so now talk about the solution for the question that I asked in the slide 1. So the solution is this, that both the sides of the quantities 1 and quantity 2 are equal to each other. And the solution and how you can do this thing is this, that just for the quantity 1, just plug f of z as e to the z in the master connection that I just talked a while ago, this thing. And for the second quantity, if you plug e to the z in the DH equality means the quality which connects between Hardy and Dirichlet, then you get this type of, then you will get the second equality in the quantity 2. So at first, again, I thought that, I don't know, I mean, whether these two things, like whether these 4 things are equal to each other or not, like whether they are equal to each other or not. So I conducted this, like I just wrote the Wolfram thing on the website, and I run, and I got the right answer. Like I got the same answer of these 2 sides on quantity 1 and quantity 2. And then I thought that, okay, so how this is happening, and I don't know, I really don't know how this is happening. I mean, I'm getting the result that okay, we have 2 different kind of series, but the summations of them are equal to each other, and it looks a kind of like a little bizarre in the starting. But I mean, if you have f of z as e to the z in the master connection, then you get this thing. And if you plug f of z equals to the e to the z in the DH equality, you get this thing. Plus, if you play with f of z is equal to cosine of z in maybe DH equality, maybe Hardy in AH equality, or maybe in the master connection, you would get different kind of summation. You get different kind of equalities, which look weird in the starting, but all of them are equal to each other. And I have played with all of that, and I haven't included in this slide because it was limited with the 20 pages in the starting. But yeah, so this was there, and I thought it was interesting to have a discussion on this. So maybe so that's why I put into the slide, and I have had this discussion. And now I wanted to have some more thing I was discussing. I was like intrigued, so I created this polynomial, this power series expansion as f of z equals to the z to the n divided by n to the s over 2. And right now I'm considering any s as like just greater than 0, and we will fix this s later on. We will just I'm just considering this thing, and with the help of this thing, I want to explore that what will happen, what we can do in this with this type of function. So here I want to say one thing, that this type of function is already considered in one of the paper of Dr. Joel, and this type of function appears in his paper was rated with polylogarithmic Hardy spaces, where he considered this type of function. So when I was doing all this thing, I wasn't sure that this has been already done, but I studied his paper in like maybe a couple of weeks ago, like 2 or 3 weeks ago. Before this spring break, I saw this type of thing over there, and I was little amazed. But okay, coming back to this thing. So we know that f of 0 is 0, and f prime of z is okay, just a little computation, we get this thing. And f double prime of this thing is again n minus 1 z to the n minus 2 divided by n to the s over 2 minus 1. So the Hardy norm of this function is going to be summation n from 1 to infinity 1 over to the n to the s. And if you look closely, this thing is Riemann zeta function for s, right? And if you calculate the Dirichlet norm of this thing, so of this function, you will get the Riemann zeta function of s to s minus 1. So now I wanted to have this connection, that is it possible to connect with the Riemann zeta function? Like something, is there any connection with Riemann zeta function also? So now let's go further and see whether we have any connection with Riemann zeta function or not. So now with the Littlewood Paley equality for Hardy, so this thing is true, and when we have Littlewood Paley equality for Dirichlet, so this thing is true. Now what I'm going to do now, I'm going to subtract this quantity from this thing and just do some manipulations and calculations and some bounding or something like that. And when we do all these things, so we get this equality in just after this subtraction. Now what I can do further is this, that I can bound this whole thing by this quantity, which is 1 over pi, the summation of f prime and f double prime whole square absolute, multiplied by 2 log over z daz minus 1, right? So now you can notice this thing, that f prime of z absolute is going to be less than the zeta of s over 2 minus 1, which is where the square is going to be less than the whole square. And similarly, this quantity is going to be less than over here, this thing, this whole zeta of s over 2 minus 2 minus zeta of s over 2 minus 1 whole square. So now with all those things, if you plug over here, right, if you plug this thing over here and wherever it's required, you will be able to get this type of equality in the raw form. Okay. Now what I'm going to do now is this, that I'm going to make it a little I'm going to simplify it further by putting s minus 3 as t, so that you can get this whole summation, this whole inequality as like zeta of t minus zeta of t plus 1 minus zeta of t plus 2 plus zeta of t plus 3 is less than or equals to this whole zeta of t minus 1 over 2 minus zeta of t plus 1 over 2 whole square plus zeta squared over t plus 1 over 2 minus 1. With a right choice of t, because we know that Riemann zeta doesn't make sense for x equals to 0, right? So if we don't make t as 0, if we don't make t plus 1 as 0, if we don't,
it should be for t greater than 1 then, yeah? Strictly for real
yeah, t greater than 1, right, would be, yeah, because you would get this thing, right?
And actually,
Right.
I mean, it seems
Yeah.
kind of good then, because then this other term, so that you want it to be.
Yeah. So that's what I was. Yeah. So that's what I was going to say, that if we plug the right kind of t, because here we want t to be greater than 1, here we want t plus 1 to be greater than 1, here we want t plus 2 to be greater than 1, and here we want t plus 3 to be greater than 1. So when we are able to choose the right kind of t from all these, like common t from all these 4 domains, so at that point of time, one can bound this whole summation, this whole stuff which is present on the left hand side with this thing. And one can see that I have derived this thing directly from this this trifecta of Hilbert space on the unit disk. So that was quite interesting. And I mean, I was exploring that, okay, where we can go further to have the use of this kind of work. So I got this kind of connection from and obviously the Riemann zeta function is studied in number theory. So maybe we can bound this whole thing with the help of this thing. And the proof is directly as over here that I have discussed, that that if you have the Littlewood Paley equality for Hardy, and if you have the Littlewood Paley equality for Dirichlet, then you can go further and you can create this kind of inequality for Riemann zeta functions involving this kind of, we have this kind of recursive relation like t plus 1, t plus 2, t plus 3. So and over here in the right hand side of this inequality, you just have t plus 1 and t negative, like half of t plus 1 and half of t minus 1. So this and the starting with this, what I mean, in the first view, I mean, this was quite interesting. So again, I thought I should have a discussion on this thing. So I mean, yeah.
Can I ask a question?
Sure.
When will the equality hold?
When does this equality hold?
Yeah, it seems like it's very vague bound.
I think it's too hard to answer when equality holds.
Yeah, I don't know when this equality hold. I haven't looked for this thing, but the inequality is perfectly true for
Also,
right kind of t. Yeah.
So another question: t has to be real though, yeah. Otherwise, the zeta.
Yeah. T has to be real. That's what I have searched for. I haven't got enough time to have a look on this whole thing. I mean, extensively. That but on the other hand, Riemann Zeta function is defined for like complex S, like complex S with the real part greater. Like if you have, like the so this is called as the Riemann Zeta function of S, right? And when you have a complex representation of S as like sigma plus I eta, so whenever the real part of S, which is sigma, this thing is greater than 0, is greater than 1, then the Riemann Zeta function makes sense. That's what I have studied in my like preliminary study for Riemann Zeta function. So it's very hard for me to say now that what kind of T I'm considering over here. But during my initial research, I considered only T greater than 1, because obviously we want to have a finite summation, we want to have a converging series. So over here I'm considering T to be greater than 1, over here I'm considering T plus 1 to be greater than 1, here T plus 2 to be greater than 1, T plus 3 to be greater than 1. So when we take the common kind of common values of T in whole this domain, all these 4 scenarios, we are good to bound this type of inequality with this thing. And the question that I think you asked, that when this equality will happen, I to be honest, in my full honesty, it's kind of hard for me to answer right now that when this thing will become total equality. So it's for it's little again a good question to for further exploration. So I'm sorry, I don't know the answer for this, that when this equality will be true, when this equality will become true. So I'm sorry, I don't know when this will be true. So moving further, so now if we talk about what is the importance of Littlewood Paley equality, so the importance of Littlewood Paley equality, okay, so the thing is this, that you guys remember that when I wrote the Littlewood Paley equality for Hardy space, I marked this thing as important function, right? Log 1 over z, 1 over absolute of z, and I said that this is called as Nevanlinna counting function and denoted by n sub phi of w, where phi is a holomorphic function on a unit disk U. And the importance of Nevanlinna counting function is this, that actually it measures the affinity of a phi of phi, that it can take the value as w in the unit disk U. So by this statement, what I mean, it means that it weighs the value w, which it in the sense that it will give large value to those values which are present deeper inside the unit disk, and it will give 0 which are present on the boundary for the Hardy space. So this is what it does. And I'm going to cite the book by Shapiro for greater details for this Nevanlinna counting function from chapter 10. But now the thing is this, that is like once we have the Littlewood Paley equality for Bergman space, or for maybe for Dirichlet space, so the question comes up that is it possible to have the Nevanlinna counting function for Bergman space or for Dirichlet space? So in that pursuit, I think the answer is yes, and this is why I'm here to have a discussion. So when I was practicing this Shapiro book from Composition Operator in 1996, I think 1993. So there's a side note which is written over there, and it says that it's possible to have a counting function for Bergman space. And it says in his note that the right kind of measure which is present alongside of prime of z squared will be called as the Nevanlinna counting function for Bergman space. And so according to this excerpt that I have taken from the book, the right kind of function which do the justice for the equality for Bergman space is going to be this thing that I have written, that I'm going to mark in this blue thing, this blue circle. So I'm going to read it for you guys, that it's a summation which you take from the pre-image of phi, which is a holomorphic map, on the unit circle, which takes the value as w, z square minus 1 of half plus log of 1 over z, and otherwise it's 0. So, but again, when I was I was studying this thing, I got one confusion. You see why? So the confusion is this thing, that is this right? Is this right kind of Nevanlinna counting function for Bergman space? Because there is some kind of confusion which is there inside the book. When I saw one more exercise from the book, which was this thing, if you can have a look over here, problem number 10, it's this equality is the Littlewood Paley estimate. It's not equality. You see there's an approximation symbol which is present over here, and problem 10 of Shapiro is trying to approximate the Bergman norm of f with this kind of thing. Here you can see that the absolute or this log thing is squared. But in my result, I haven't squared. I have created the equality with the right multiplication of this measure. And which is why I mean, and from problem 10 to from problem 11, this m phi, this, like when you do the composition operator, this m phi is going to be the Nevanlinna counting function for Bergman. So I think that the counting function for Bergman norm should be this thing, because I have the equality instead of the approximation which is present in problem 10 for Bergman from Shapiro, and from his statement also from this counting function on page 196 you can see. So I draw this conclusion that that the Nevanlinna counting function for Bergman norm, for Bergman space, should have to be in this manner, that it should have this absolute of z square minus 1 over 2 plus log of 1 over z, instead of having log of 1 over z squared. So I hope you understand my point over here. What I want to say, with all due respect to Shapiro's work and everybody's work, is this, that I have the quality of Littlewood Paley Littlewood Paley equality for Bergman space, and as Shapiro already said this thing in this excerpt, that when you have kind of suitable measure multiplied by f prime of z squared, that particular function is going to be the Nevanlinna counting function for Bergman space. So when we have this equality, which I have done over here, which I was discussing since the starting of this presentation, so this should be the Nevanlinna counting function instead of that. So this was my whole personal tussle, that which one is right, what is right. But according to me, I think this should work well. This should be right. And when I studied further, I haven't got the right kind of work online. Maybe because people, I think, with all due respect of operator theorist, I think people don't know about Little Paley equality for Bergman. I don't know whether this is right or not. Maybe this statement could be a little strict or hard, but I think this is my improved result from Shapiro, and so this should be the Nevanlinna counting function for Bergman norm, for Bergman space.
Which
So
Shapiro?
yeah,
Which Shapiro?
Shapiro 1993.
What's the first name?
Joel Shapiro.
It's a Joel Shapiro. He
Okay.
was at Michigan State. He's retired.
Yeah. So the book that I'm using is, I think it's 1993 publication, and obviously I have cited. Everybody now knows from which page number I'm talking about. So page number 196, and page number I don't know. This is I think page 195 or page 194. So I don't know what would happen for Dirichlet space, because I don't know why I haven't. To be honest, I haven't worked with the Dirichlet space, I don't have any specific reasons for this. Maybe I will work in the future time that what could be the Nevanlinna counting function for Dirichlet space. But side by side, I was working for creating the Littlewood Paley equality for ML2 space for ML2, as I said earlier. So again, I got this has to be the Littlewood Paley equality for ML2 space for Dirichlet 2 space, and I'm going to read it over here. That the Dirichlet norm for function which belongs from ML2 is going to be equal to f of 0 squared absolute plus q over pi, and you take the integration on the whole complex plane f prime of z squared multiplied by this quantity with respect to the area measure. So and this is kind of a corollary, as I said earlier during the starting of my presentation, that when you plug q as 1, you will get Fock space. So if you want to have look on the Littlewood Paley equality for Fock space, this is going to be the equality, right? And now I'm going to give the proof for this kind of equality. So it involves the Fubini theorem, nothing new. And obviously I'm doing the step by step. And here, Nathan, as you said, I'm sorry, I apologize that yeah, it involves integration by parts, but obviously you have to do the conversion from complex coordinate to polar coordinate system for further simplifications, you see. So for when the function is in the Dirichlet space, this structure, the function, the structure of f becomes like this, the norm become like this, and you can write down, obviously you can write, you can break all this thing is in like a0 squared plus the summation from n from 1 to infinity, and this is a gamma function, gamma qn plus 1, right? So now this is the left hand side. Now talking about right hand side, we have right hand side as like this. So f prime of z square will become summation from 1 to infinity n an z to the n minus 1, and you still have this thing. Just continue play with the right kind, with the careful use of Fubini theorem. You will be able to you will be able to interchange the order of the integration with respect to dt and dr. Make sure what is t. I think t is already discussed here. So you will be able to get this whole thing over here, and the result is established. So this is the Littlewood Paley equality for Dirichlet space, and again, if you plug q as 1, you will get a Fock space. So as of now, from like till this point, with the help of this presentation, everybody knows now what is the Littlewood Paley equality for Hardy space. Everybody know for Hardy space, for Bergman space, for Dirichlet space, for Dirichlet space, and for Fock space. And now when I was going further, when I was studying further, so I wanted to have the next question that came in my mind is this: that is it possible to have the Nevanlinna counting function or counting function for Dirichlet space or for Fock space? So the question, like, this is still open for me, in particular for like research work, and the problem that is coming up is this: that I have to create the zero sequence lemma, or zero sequence lemma, or I think zero sequence theorem for whole complex plane, because we know what is the zero sequence theorem for the unit disk. If you the zero the zero sequence theorem for unit disk, it says that if you have zeros of f and it converges, then is the result look like this thing: 1 minus z to the n is less than infinity, something like this. So I mean, it's going to be hard to prove this kind of result.
First of all, it's only for Hardy space. It's utterly false for Bergman space.
Okay, it's true for a Bergman space or for Fock space, right?
No, it's not.
Can you please pardon? Can you please say one more time what you said?
In the unit disk, if you have a function in Bergman space, it has
Zero
it
sequence
can
lemma.
have, yeah, zero sequence lemma is false. It's only true for Nevanlinna class, which is a little bit bigger than Hardy space, but it's not true for Bergman space. Bergman functions are not functions necessarily in Nevanlinna class. You have to be careful. And as far as Fock space consists of entire functions. So why don't you use just Nevanlinna characteristic? It's perfectly well suited for entire functions.
Okay, so yeah, thank you. So yeah, this is what I mean.
Well, it's true for Hardy and it's true for Dirichlet, which is a subset of Hardy, but it's not true for Bergman at all. The problem of what are the zero sequences for Bergman function is wide open and probably will never be solved, and it's very, very difficult.
Okay.
So what is known about zeros in the Bergman space? Anything, or you're muted?
I have no idea that.
But you're muted. We can't hear you.
If you have a Bergman function, which is also in Nevanlinna class, which is not given, then that Blaschke condition is true. But Bergman functions are not in Nevanlinna class. They do not have generically boundary values. And in particular, their zeros are very mysterious. And if you look at Hardy spaces, the whole space scale of Hardy spaces, because it's not only H2, it's HP.
Yeah.
You just integrate pth power. All zeros, because all of them are subclasses of Nevanlinna class, which has bounded characteristic, which is wasn't written, but it's easy. It's log plus of the absolute value of the function. Then all of those functions, if the sequence of zeros satisfy Blaschke condition unless the function is identically zero. For the Bergman spaces, you can not only consider A2, but AP for you just integrate pth power with respect to the area. And it's known since thesis of Charles Horvitz from late 70s, he was a student of Peter Duran, that for every P, there are different zero sequences. It's a very complicated problem. It's not going to be solved in our lifetime, I assure you. I mean, there is necessary and sufficient condition done by my colleague in Arkansas, Dan Looking, about 20 years ago, but it's untraceable. You can't trace it. So nobody really understands the Bergman sequences. However, you can, it turned out, that's what we did in the 90s, a bunch of people. You can find something like Blaschke product, like products, like contractive divisors. You can divide out zeros in Bergman spaces without increasing the norm. Because Blaschke product has absolute value 1 on the unit disk, on the unit circle. So you can always divide a Hardy function by a Blaschke product and get a function with the same norm without zeros. In Bergman space, you cannot get the same norm, but you can get a smaller norm. You can construct those, they're called contractive divisors. I mean, it's the whole theory. It's basically, it's.
So in conclusion, it's hard to find the zero sequence for Bergman spaces, right?
Okay.
Well, there are necessary conditions and sufficient conditions, but they do not meet at all.
Okay.
Okay, so
yeah, so
Any further
Yeah.
questions for Himanshu?
Yeah.
If not, let's thank our speaker.
Thanks.
So, next week, I think we have Sherwin Kuchekian talking. So I have to schedule
I'm
with him.
sorry, who is talking next?
Sherwin
Who?
Kuchekian.
Sherwin?
Uh-huh.